So this question, you have a mass on a string, let's say, and it is swinging around in a horizontal circular path, and the two forces on the diagram for part A, first force is mg acting downwards, and the second force is tension in the string acting in the direction of the string upwards against the weight. So those are your two forces. Now we can split that force into two components, t cos theta and t sine theta. Theta being the angle from the vertical. So if you do a little bit of trig, you can see that this angle here is also theta. So therefore that is t cos theta and that is t sine theta. T cos theta is responsible for keeping this bob stationary in the horizontal. Therefore the net force in the vertical is 0, and the downward force mg is equal to the upward force t cos theta, and I'm going to rearrange it to get t equals because in this expression here that we are trying to derive there is no t, so I'm going to make it equal to t. I will explain later. Horizontally there's only one force, which is t sine theta. So that force t sine theta is acting towards the center of the circle, directly towards the center of the circle, and that is providing the centripetal force. So the net force of t sine theta is causing this object to move in a circular motion. So t sine theta equals mv squared over r. Because this expression looks at angular velocity rather than tangential velocity v, I know I can write mv squared over r in a different way, which is m omega squared r. So I'm not going to use mv squared over r, I'm going to use m omega squared r. So t sine theta equals m omega squared, and rather than write r, I've written it in terms of L. And how have I done that? I know that length there is the length of the string L. I know that the angle from the vertical is theta, and if we go down from that position, that's the center of the circle, so that horizontal distance from there to there is r. So I can create a right angle triangle, and that radius r in terms of L is r is equal to L sine theta, and we see that this has an L in it, not r. So I'm going to replace the radius with this L sine theta, and therefore rather than write r, I've written L sine theta. So it's m omega squared L sine theta, and as we can see, that force t sine theta is responsible for this circular motion, this net force m omega squared r, and we can see the signs cancel, and we end up with this expression that tension is equal to m omega squared L, where L is the length of the string. Now I wrote down the expression in the vertical direction in terms of t, so what I'm going to do, equate, and I end up with mg over cos theta equals m omega squared L. I can see that the m's will cancel, and what I'm going to be left with is g over cos theta equals omega squared L, and we got to make it into the subject of omega, so I'm going to divide by L and root, and I end up with the angular velocity is g over L cos theta. So how do we set up this question? First of all, we need to get the components, vertical and horizontal, of the tension, and that's t cos theta, t sine theta. We need to write r in terms of L, so that was L sine theta, and we need to look horizontally. There's a net force of t sine theta, which is responsible for circular motion, and then vertically there's no net force, and that is responsible for the object remaining in that position in the vertical direction. Combining those two expressions, I end up with omega equals root g over L cos theta there.